I'm going to start by describing the first right-hand rule, which is a way of figuring out how a conventional current, not a flow of electrons, generates a magnetic field and the direction it goes. If you were to wrap your right hand around this wire and point your thumb in the direction of the conventional current, your fingers would be pointing in the direction of the magnetic fields. And the further you go, then the less strong this field is. That's represented by that D there. The stronger the current through the wire, then the stronger the magnetic field. Now, if you wrap this in a loop, you would actually create this adding effect where it goes through the loop like that and it still goes around, and you would represent that by that. As you can see, this constant is in both equations. That is that right there. Now, if you were to wrap that into a solenoid, it would amplify that effect with this equation here, n being the number of turns per length. That's represented right here, so you can also represent this right here. As you can see, this mimics a bar magnet's magnetic field lines. It's a very important concept to understand. Okay, now I'm going to explain the second right-hand rule. Now, if you had a particle, let's say it was positive and it was coming toward you, this is because we think in conventional current when doing magnetic fields, if it was coming towards you and there was a magnetic field, then a force would go down. Now you can picture that force being pushed with your hand, that current with your thumb still, and the magnetic field still with your fingers. The only thing different is the force is pushing with the bottom of your hand. Now the strength of that force can be derived with this equation here. So the larger the charge, the larger the velocity, the larger the magnetic field, the larger the force. Now if you were to have a particle immersed in a magnetic field, it would actually travel in a circle. You can find the radius of that circle with this equation here, just using that centripetal acceleration formula. There's plenty of videos out there to figure out that, so that's as far as I'm going to go into that. Now, if you were to have a wire immersed in a magnetic field, it would still be forced down. Now, you can figure the force of that, and the force equals BIL, or force equals Bill, is the way I like to remember it. Now, if you were to have a coil, or an armature, going through a magnetic field, this side would be forced up if the current was going this side would be forced down. If you were to switch the direction of the current, this side would be forced up, and this side would be forced down. Again, that's a very important concept to understand. So if you were to have this set up, as soon as this was vertical, this would still be forcing up and this would still be forcing down, which would make the motor stop in that vertical state. So if we have that same setup, we need a way to switch the current so that then this switches, rather than going up, to going down, or vice versa, whichever way it's spinning. Now the way you do it is you have two brushes connecting the current, so it would go in this way, and then it would go around the armature and out this way. And then as soon as it gets vertical, there's a little gap here that would switch the direction of the current so that it keeps spinning. Now, a way to maximize that is if you were to add more armatures, you could add another one, you could add 6, 8, as many as you wanted. It would have a smoother transition and you could maximize where that force is the most. Another way to strengthen that is if you were to get a little wire and you were to wrap it around many, many times and then come out this way and have that same armature setup. Now, you'd think that has more to do with the solenoid and maximize the magnetic field, but it actually just adds more length in that magnetic field to be forced down, increasing the force on that armature. And that's how you maximize your motor. So my original plan, and my plan throughout, was to have 3 armatures. But my original plan was to line the magnetic field up there so that it would want to line up there. Now I think that was a flaw because this force isn't really maximized because it's pointing up at kind of an angle. And I'll go through torque later to describe why that is. But here, it's pointing down. So I decided to switch it so that it was firing at a different spot so that the torque was greater. My plan for connections was it would go, fire 1, 2, 3, and then the current would switch 4, 5, 6, and that ended up working out pretty well. So the equation for torque is torque equals length force sine theta, meaning the longer the length, the more torque if you apply force. And if there's an angle, then you're getting less force out of that angle. It's actually usually cosine theta, and that angle's on the other side, but it doesn't really matter in that way. So this would apply more force than this. So right now I'm working on the 3rd version of the motor, because I learned a few things throughout, and the first 2 didn't work. This is the first version here. The most important lesson I learned here was how important a good connection is. These copper plates actually didn't end up conducting electricity very well. I'm not even sure if they're copper anymore, but they probably are, but they're not very good conducting copper if they are, which doesn't make sense. So I used these wires instead, which are very good at conducting. And I made part 2 focusing on getting just good connections and organizing it well. Now part 2 was originally these 2 parts were attached. So this is the motor here wrapped around in 3, and then this was the commutator. You can see it had really good connections, and I was able to get current through every single one, at least most of the time, which was good, but this ended up being way too bulky. I realized that the friction that the brushes had is going to be high no matter what, but on here especially it was extra high, not only because these connections were really messy, but because the radius is so large, the torque is a lot caused by the friction. So I decided after some research that a better option would be just attaching it to the sides like this. It's much simpler and it's much smaller, so the torque caused by the friction will be much less. So the equation for torque is torque equals length force sine theta, meaning the longer the length, the more torque if you apply force. And if there's an angle, then you're getting less force out of that angle. It's actually usually cosine theta, and that angle's on the other side, but it doesn't really matter in that way. So this would apply more force than this. So that's the plan for the new one. Oh yeah, there's one more thing, is there's no current running through this, but the magnet actually attaches to it because I used a what's that called again? A bearing to attach it to it. It's not actually being used as a bearing, but it was being used as a base, and that's not going to work because it's magnetic. I think that was interrupting the flow. So before I move on, I want to make a comment on just what everything's called, because I didn't really cover that, and I've been calling it by its proper terms. The armature is what spins around the axle, which is the center bit. The commutator is what's attached to the armature that makes contact with the brushes, creating current through the whole thing. The stator is the two magnets that force the armature around in circles. So version 3 is going to look pretty much the same, like this. It's the same as what you just saw. It's going to be 3 around. As you can see here, coils are going to be wrapped around this way. They'll probably be wrapped just this way to be consistent, but I drew a little diagram here to show how it's going to kind of run. So as you can see, positive will come through here, negative there. This is the brush. The brush is just going to be one wire. So when it's connected to this one, as you can see, it'll be going in this way and out this way. Negative side of the battery's over here, positive's over there. So it should rotate this way, at least enough to point this one up to the side there. Now this one actually has to have the opposite current. So it's going to be in that way, out that way, and it's going to rotate this way. And then you can see this one has the same current here because it'll be going the same direction. Then obviously all of those will switch, reverse, and it should just keep spinning like that, the magnetic field going that way. So that's the plan. Now this was originally going to be life size, but I realized my magnet here is actually the same radius as that. So this is just like barely going to be in that magnetic field. So I decided I'm going to size it down. I'm going to try to make it really small. That'll allow me to do a lot more loops, which will take a long time. But I'm going to try to fit it on there, which is the smallest I've done so far. I also wanted to make it pretty long because I wanted to have a lot of space in that magnet. I wanted to have more length. So it's going to be pretty long. It's going to be the same, or I think even longer than it has been before. So hopefully that'll work out pretty well. So step 1 is going to be to cut these pieces. This is 1 centimeter by 6 centimeters. Now it will depend on a couple things. The 1 centimeter is for folding, so that'll leave about 3 millimeters for each fold, which will turn it into this like mostly square shape. I'll fold it along that way. This is where the solenoid is going to wrap around. The length is actually 2 of the length of these pieces, and then 1 of the length of not the full diameter, but as you can see, it's a triangle, so it's going to be about, So there is a good way of finding the length of those pieces. So first, just draw, and measure these lines as well. Let's say this is 1 centimeter, this is 2 centimeters. So you'd want to draw a line to the center that's squared in the middle of that. And in the middle of this one too, you'd want to do that. And you would get a dot in the center where those two meet. You could do 3 to get it more exact. Now, after you have the center, you want to use that circular piece to do the center on that line and the edge on this line, and you'll get a circle, right? And once you do 1 circle there, then you do another circle right there, and another circle right there. And you can do that pretty easily with whatever piece you're using. And then pretty much where the centers are, because that's where you're doing it, you get a good triangle. And that's the length that you want to multiply by 2 and add to get to that piece I just showed you. So once it's all folded, it should look like this. You can see it's like most of a square, and that's perfect. Mine are pretty even. It's about as good as you're going to get. You can make this width longer, and it'll be easier to fold, and you'll also have more room for wrapping the coil, which is very useful. So if you need to do that, definitely do that. So you're going to have 3 of these in total. Next, you're going to cut little slits, like 1 centimeter and 2 centimeters, then 1 centimeter, so that you can fold it to wrap around your cylinder. As you can see, it doesn't really wrap fully around. That's okay, because it's going to be taped together, and that'll kind of fill in those gaps there. I'm going to do that all the way around so it wraps really nicely. This one fits, so if you want to lengthen it a little bit more, add like a millimeter or so for each turn. That's probably best. I've done that in the past. This one I didn't really bother, although I probably should have. But that's what it should look like. It's about that. Okay, so after you wrap it in tape, it should look like this. You can see I'm just getting a small piece of tape, and I'm first putting it on there, and then I'm using some scissors to fold it onto itself. Now this looks really, really messy, but I'm gonna get some scissors and I'm gonna cut around where it doesn't need to be, kind of not on the plastic. And I filled that gap right here. It's this one here. You can barely tell, which is good. You'll probably be able to see a little bit more once I clean this up. So let's do that. So that's what it should look like after you've cleaned it all up. And yeah, so I cut the inside and the outside. That's the side there that I had to kind of connect. And you can see that if I push this in, it fits pretty perfectly around there. Once I glue it on, it will be a nice, snug, perfect fit. I didn't mention before, but these are actually from just like one of those raspberry containers or blueberry or whatever. I just cut it out. You can also use like gift cards and stuff like that. That'll also work pretty well. But yeah, that's where I got this. And when you're folding them, try to make sure that there's no like loose parts, because the solenoid will get caught while you're wrapping it pretty easily, and you kind of want it to be as clean as you want. Like, see, even that thing, like, you could snag on there, so I'll try to tuck that in. But yeah, there you go. So now I'm going to connect all three with a piece of tape like that. The last one don't connect until it's a round thing, and then I'm going to carve a little bit more off. So you can see it's a kind of a tight fit, like they don't all fit perfectly well together, but I'm going to cut this outside end off here so that I can kind of push them together a little bit better. That'll also make it easier to wrap. So I skipped a couple steps there. The first step is I glued 2 pencils on each side. That's where it's going to rotate on. It would be better if you could drill a hole through and then stick the pencil through, but I don't have a drill. And then I wrapped my first coil there. It went in on the left side there, and it comes out on the right side. And now I'm going to solder/glue the last pieces on the commutator. I also need to sand the ends of these to get the enamel coating off so that current can run through it. Okay, I've attached the motor to this. I tried to make a brush there, but it's bad, so I'm going to make a new one. But first, I'm going to mount the magnets on these things here, and then I'm also going to reconnect things with these things here. And yeah, I'm also going to wrap this to make it a little bit tighter. Okay, so it's a really tight fit, but the motor still spins pretty well. Eventually, if this thing gets going, I think to fold these in, create a little bit more space, I can push it a little bit more. That would be better, just so it has more room to spin. This thing's a little loose, so I can just adjust it later, but it's gonna work for now, just testing this thing out. And yeah, so I would get this thing running right now, but that battery won't stay connected. So you guys are about to figure out what the most annoying thing with this project is. Not figure out. You get to share the annoyance now, because now I'm just wasting time talking about it. And that's all this connection has done, is waste time. Okay, so there is the motor inside of the something that starts with an S, and here's a better, more reinforced battery. I've got 6 volts made with 4 cells, and got a pretty good current going through there. Obviously can't measure it because it's higher than what that scale can read, but yeah. And now I'm going to start making the brushes. That's what I got these bad boys for, so pretty much just going to set them up like that, or no, not like that, like that, and then it should be able to spin pretty nicely. Yeah, so that worked out pretty well. I really like the way that's connected. Like, it doesn't take much force to spin this. I might have to make some tiny tweaks and make sure that they're both touching the right sides at the same time, but it actually looks like they are, or at least they're pretty close. So this is the best setup I've kind of had so far, and I'm running the most current through it than I have yet. So hopefully I'll get it running. So pretty much I got this spinning a bit. I would show you, but I think I lost connection somewhere in the battery. So I just need to fix these connections because it wasn't really spinning all the way. As soon as it lost contact, it stopped, and like it's got some momentum there, but apparently not enough. Maybe we'll have to up the power, and maybe it's fixing the brushes, maybe it's a little bit of both, but getting close. Okay, so I've cleaned up my design here a little bit. I've attached it to this board, so it's a lot sturdier now. I can get a lot closer and work with it really well. All this is pretty permanently attached. I've re-glued that because it came off, and now I'm in the process of gluing the switch to the board, and I've set the battery up like this so it kind of holds itself together with gravity. This connection has been real frustrating. I finally figured out a way where it kind of held, but we'll see if that causes any problems later. Just gonna work on the commutator. Oh yeah, this is called the stator. I remember what its name is.
Just gotta work on the commutator. When this rotates, it kind of rotates out and in, so it's not gonna be as simple as just 2 wires. It needs to be something that actually shifts back and forth, and I've got a plan for that. Yeah, so if you're designing this, try to keep this as straight as possible. It could be better if you could drill a hole through here. I didn't have a drill at the time. I would have if I had a drill press, and then stick a pencil through, or whatever you're using as the axle, sticking the axle through. That would probably be a lot better than what I've got here. I've got 2 pencils on each side.
So this is the best run of the motor I got throughout the whole testing. Try to listen really closely to the sound of the motor because it sounded really cool in person.
Oh, that's the best I've gotten so far. That's actually the best I have gotten. Wow, that was great. Okay, so finally I have created the final product of the generator.
Let's go backwards for a second.
So there's something in physics called magnetic flux. The way to find magnetic flux is it's the B field that goes through an area. Now why is that important? Well, let's say we had a loop and we were spinning it, looking at it from the top. It would look like this, and this, and this, and quickly this. There would be a change in magnetic flux. Now, it happens that a change in magnetic flux can cause a voltage using this equation here. So the faster the magnetic flux changes, the more voltage is created, or we use this symbol, standing for EMF, or electromotive force. The equation is actually this, n being the number of loops, and the negative just representing the direction, and this makes sense. So, if we were to have a loop, and we were to all of a sudden add a magnetic field, then the universe would want to actually resist that change and add another magnetic field going the opposite way. That would induce a current. We can use the right-hand rule to show which direction the current goes. If you were to take that magnetic field away, the universe would want to add magnetic field, meaning the current would go the opposite way. Now, again, the 2 ways to change magnetic flux is to change the magnetic field or change the area, like we went through before.
So if you're ever wondering how generators actually generate electricity, that's how.
It is the exact same as the motor, except here I've got this commutator set up. You probably saw that earlier in the video, unless I didn't put that in. But what that does is I've got the wire coming through the top and the bottom, just touching those. Now, the reason I couldn't get the motor spinning is this created too much friction for the motor to power. Maybe if I had added more batteries, it could have done it, but I didn't want to create a short circuit while, trying to run more current through my thin enamel-coated copper wire. So I didn't put more batteries on to that. So I turned it into the generator. The friction doesn't matter as much because I'm the one spinning it, and then it will be creating current. So pretty much spin this. I've got a little nub. The reason the pencils are there is it creates more mass on the outside, which keeps it spinning a little bit longer, so I can more easily read the top values. So far I've gotten about 5 amps. I'm going to try to get 10.
So while spinning my motor, I managed to get an average of about 5 hertz, which is equivalent to 300 rounds per minute. Then I grabbed the drill. No, I didn't. Yes, I did. So before I show you what it looked like for me to spin this thing with a drill, I'm going to show you this. I was able to get an average of 0.1 volts and 1.1 milliamps. Now those values aren't definite because these old scales are very hard to read, and I'm not sure whether I was doing it right. But I'm going to try to prove these values later, hopefully. This is me before clamping it down. Definitely clamp it down.
Okay, that's looking better. Yeah. Oh, broken now.
So, I do wish that I could do math with that value with the drill, but it's really hard to tell what the rotations per minute or hertz is when spinning it with a drill. First of all, I wasn't recording it at the same time. Second of all, this is the video going very slowly, and it's going to pick up speed in a second. It would be pretty hard to count the rotations per minute. I could maybe count the amount of times that black piece of tape goes by, but even that's really, really hard. So, unfortunately, I'm not able to do that. Now, I will say that spinning a not straight axle with sharp pencils attached to it with a drill is a terrible idea. And you're going to see why in a sec.
that pencil probably could have taken out my eye. So after all that, I decided to attach my motor to 9 volts. And it span pretty easily. It's a little bit finicky, but it was way easier than with 6 volts. So I was pretty happy with that. And then I had a really good idea to attach it to 12 volts. And 12 volts was very easy. It could run consistently, constantly, and that was great. So then I decided I wanted to hook it back up to my commutator. I got this really, iffy design, and I would test the wire by tapping it against the metal to see if a spark happened, and if it did, I knew there was current. And then I finally got it going with a lot of tinkering. Now, this was the only time I got it running, and I got it running for a great amount of time, and it shows that if I had just put a little bit more attention into certain things, I would have had myself a motor. And then the wire slipped.
So I found many approximate values, such as these ones. So as you can see, this is my EMF that I measured from my generator, which was 0.10 volts, and the current from the generator, which is 1.1 milliamps. Maybe. Now, I wish I had a better scale, because I don't actually know if I was reading them right, and I definitely wish I either learned how to read them or got a scale that I could read. With these values, I could find the power and the resistance with my generator. Now, this page, which I'll make sure is in order, is where I found a lot of my areas and stuff. I mean, there's a lot of extra paper where I actually found it. This was pretty easy, it was just measuring directly off, but the area I actually found with an average area and then a calculation on minusing the corners, turning them into a round area. And I ended up with a shape that was very, very similar to what most of the solenoids looked like. I'm about to mention them in the video, but I accidentally called that area the commutator area instead of the armature area. I also found the average commutator area, which was 245 millimeters squared, the average length that was effective in the field, and that's per turn, which was 23.5 millimeters. The average amount of turns was 118 or something like that. It's kind of hard to count, there's a lot of them. And it was 5 rotations per second, which is 300 rotations per minute. And the average radius, and that means, if we had our motor, and this was where the force was acting, and this was the center, that's the average radius, 11.5 millimeters. Now, there isn't actually much that you can find with this. I was definitely missing some data, and I'm going to go over what specifically I was missing in a minute. But first, what did I find? Nothing, except a very theoretical magnetic field value. Now, I did that with this equation, which we went through earlier. EMF equals number of loops per change in flux divided by change in time. Now, you can change that into B times area, which is the flux equation, and you can change in time to, well, the time is 1/6 of the period. The period is 1 rotation, and that would be 1/5 of a second. And it's 1/6 of that, so you have to put the 6 up there because the T is down there, and I changed that to that. And that ends up looking like this. So if you want to solve for the B field, this would be the equation here. Now, putting the values I have in there, now keep in mind, this is actually translated into meters squared, so it's a very small number. The angle is the angle that area starts at, so you're not seeing the full area like that. The B field is actually only seeing an area like that in this part of the rotation that I actually considered. And I ended up getting a value of approximately 0.23 T. Now, it actually ends up being exactly that with these numbers, but the reason I did approximate is because all the values up there are very approximate. Now, I actually went online and found some values for those units for B and V, and it turns out that the units in this equation actually work out for a B field. So that makes me a little bit more comfortable that this could possibly be at least near the actual value of my B field. Now, if I have the proper value for the B field, that means there's other things I can calculate as well, or at least I could have. I could use the F equals B times IL, or F equals Bill, but that current would have to be the current for the motor for me to figure out the force that the magnetic field is generating on each of the lengths. Now, you would multiply it by N because it's applying that force to every single one of those turns. So it would actually look like that. Now, with that force, you could actually find the torque, because torque equals force times distance, the distance away, which is that radius I talked about earlier, and it would be the average distance times sine theta. Now, that sine theta is actually the angle at which that force is acting. As you can see here, that force wouldn't be directly on there would be an angle involved, and you would use this. What angle would you use? You'd use one of the angles to find this. Sometimes it's sine, sometimes it's tan. It really depends where it is. The only reason I didn't do much more of this, I tried, but it's because this, first of all, is constantly changing, so it takes calculus. And second of all, I don't even have the current that I needed, the current of the motor. Now, if I were to have that, if I were to take data that I didn't do, I could use this equation, first of all, or at least hopefully I could. I would try to find a value for torque. I would measure that by simply attaching some sort of rod to the axle, turning it on, and then it pushing down on a scale, and that scale would give me the force, and then I just have to take this distance and do that to find the torque of that. And then I could confirm all this data with that value. I could also confirm the V value with this torque value. So if I could do all that, I would do it, but it gets a little bit more complicated than that because there's different torques in different times, and they're constantly changing. You'd have to use calculus. There's also the force of friction. Now, there probably wouldn't be much friction because it wouldn't really be moving, but there would definitely be friction caused by the brushes, so I'd have to take that into account, which would be really, really hard to take that into account. So I don't really know how I'd do that, and I probably wouldn't have had much time to do it anyway. So that's about as far as I got. If I were to mark myself on, my data taking in this process, I wouldn't give myself the worst mark in the world, but there's definitely stuff that I wish I measured, especially that current through the motor. Definitely should have measured that. And if I had been able to do all this, I would also measure the current at this point when I'm measuring it, because that would make me able to calculate the back EMF. So there's a few main ways to design your armatures. One of them is, the automatic way you think, and that's to make it so that they cross over each other like this. But when making this, if you have a bunch of wraps, it's really hard to set them up like that. So that's why this design doesn't really work that well, although it is very direct in the way the forces will act on it. The second design is like this, like very long loops, and although the force works pretty well, it doesn't really maximize space very well. It's very long, and it's very, you're not using much space. And it has a huge radius, so if you have small magnets like this, it's not always going to be in that magnetic field, and that's why these lines would be pointing like that. If you had a bigger magnetic field, it would fully be in it, but you still wouldn't be using a whole lot of that space. Now my design, like this, which even through research, trying to figure out a design better, my design still seems to be the best. Seeing people recreate it, and seeing that most motors end up being designed like this, because if you have a small one, you can really fit a lot of wires in there. And if you really want to maximize this, you actually want to mix these two designs together. That means, let's say the magnet was this big, you could barely rotate in there. You would actually want to just wrap more and 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 more, so that you get this triangle shape, right? And if you had 3 of them that ended up with these triangles, you'd be using all of your space, and you would have as many loops as possible in that space. Now, that's one way to maximize it. Another is to get stronger magnets. You want to try to make them as close as possible, that kind of thing. And this design would be the same thing. You'd be trying to maximize it, and that's why this design and this design don't actually have a huge difference in torque creation, because you want to try to get as many loops as you can. You don't have that many loops. Obviously, there's better ways to wrap it. Like, you wouldn't want to just wrap all of them really close inside here. If you would either want to wrap them all out here like that, or wider out there like that, right? And there'd be better ways of doing that, and more space. Now, one of the main ways I learned how to maximize a motor's potential is I was really restricting myself, and this works for a generator as well, to one of these coils had current running through it once. But as I learned, there's actually a way to make it so that there's always 2 of these working, so that you're getting double the force, double the torque, or at least close to that value. And I'm going to show you how to do that now. So the way to make it so that 2 of them are firing at once is you would actually have 3 rings around the commutator, rather than 6, and you attach them like this. So at this point, there actually wouldn't be any current going through this ring, which isn't a bad thing, because there is a time where you don't actually want current to be running through a ring, because it's just going to work to stop the motor and slow it down. And there's actually a little bit of a range of motion where you don't want it to be working, but that's why that's there. It's not a bad thing. There's a time where you don't want it to be fired. Sometimes in this rotation, all 3 of them are firing. So once it rotates and this one becomes in contact, it'll go all the way through here, it'll go through this armature, and then it'll connect into there, and then it'll also go into this armature and connect through there, so the current will be going in the opposite direction. Now, organizing that wiring is obviously going to take a little bit more thinking, but there is a way of wiring it so that they're always firing at the right time in the right direction, and it's always working with you. And that is a great way to maximize the amount of voltage you're either creating with a generator or using with a motor. It doesn't waste as much as just using one. So this is what I'm going to call if I were to do it all again. First, I would start with the brushes in the commutator, because that's where most of my problems happen. Tools required would be pliers, drill, material would be high gauge pliable copper wire, which I actually had and I used as the commutator before, and something like a toothpaste lid, just so you could drill a few holes in it. And you'd also want to drill a hole through here, so you'd also probably need, you need a drill, I said that. So you drill a hole through here, and you'd actually make it go lengthwise like that. So rather than, it being a bunch of round things like this, which mine was, it would be straighter, so there would be a lot less friction. When I did that, it would be a smoother transition. And as you can see, there's 3 here rather than 6, but these would all be connected from here, and then you would connect that to the loop like I showed in the other video. Now, you'd also want to make sure this is all spinning very straight. That was a big problem that I didn't have. So the brushes, all you'd really need is, saw, sandpaper, wire cutters, stuff like that. A carbon graphite brick for materials, springs. The lower spring constant you have, the better, and good conducting insulated wire, which is what I used. And the more you have, the better, because the more wraps you can make. And maybe some high gauge copper wire, just in case you run into something. But pretty much what you'd want is this wire running all the way through the spring, and these are those carbon graphite bricks, which you usually use in this. Now, what I would actually do is I would leave a gap in here. And another thing I saw is you would have something like a screw here going all the way through, maybe a screw here, so that you could actually tighten and loosen these. Because then if you had too much friction caused by these brushes, you could just loosen the screws off a bit, and then your motor would get going. And then let's say the brushes got worn out, because they do, and your motor stopped working. Just tighten the screws off a bit, and then your motor could keep going. Now you'd want to design something like this with some springs, and you'd want to attach it in here, right? And you'd want to find the right spring constant, but it wouldn't matter as much because of the screws. And that would probably be the best design for your brushes, or at least something that you could make with just, wood and all these simple materials. You could even use a spring like from a pen or something like that. Now the last thing is the armature. I already designed how you want to wrap it, but what I would do differently is I would actually do a triangle prism, and then I would just get kind of rod, and I would just begin wrapping, and I would measure the amount, the kind of diameter that you would want this wrap to go, and I would just wrap it until there. Obviously there'd be some planning, but then I'd do that again, and I would do that 3 times, so I'd be really maximizing that space. It would all just be wire there, meant to create power. And then after doing 3 of those, I would then attach each of them one at a time, because they would kind of be, this shape here. Ignore this is kind of where I was planning that. It would be this shape here, and then I could just, glue them on right there, or something like that, or even screw them on, or whatever, right? I could attach them after. Then I wouldn't have to deal with that awkward wrapping and the other wires getting into place and it being, kind of weird. It'd be a lot easier just to wrap it and then attach it. So you'd need a good piece for that, but that wouldn't be too hard to make with wood or 3D printer if you have access to it. Same for this. A wood or 3D printer would probably be even better.
I had a lot of fun building this motor. In total, it cost about $100. I found some of the receipts, but it cost about $100. A little bit more. You could definitely make a decent motor for like $50, and if you wanted to make a really good one, it'd be approaching $200. But again, I had a lot of fun. That's the end of this video. Have a good summer.